Well, if we're going to have all the presentations in the same class.
It's fine. Welcome to the probabilistic planning session, and Felipe will go first.
Okay, I'm going to present a joint work with Manuel Veloso, my advisor at Carnegie Mellon University. Before I start my talk, I have a quick announcement. So unfortunately, the version of our paper in the thumb drive and the CD runs the wrong version of the paper. So if you see this picture in the front page, you got the wrong version. In the online proceedings, we have the right version, or you can just Google short-sighted SSP, and you're going to land in my page or in the right version of the paper. So, on probabilistic planning, we have two classes of solutions, right? One is the complete policy, that it's a mapping from every stage to an action. And the good thing about the complete policies is that it will never fail. If you give this complete policy to a robot, the robot, no matter where you end up, will always know what to do. The other thing that is good about complete policies is that they can be optimal. The bad thing is it does not scale up. The other class of solution are the partial policies that map some states to action. So the bad part of it can fail. So if you give it this partial policy to a robot, the robot might reach a state that is unpredicted, and we might need to replan, might need to call the planner again. The other thing is partial policies are non-optimal, but the nice thing about the partial policies is that they scale up really well. It's computationally efficient to find one. So in this talk, I'm going to present a framework that gives a new trade-off between complete and partial policies. And this framework is composed by two parts. The first one is a new model that we call the short-sighted stochastic shortest path problems. The second part is a new planner that we call the short-sighted probabilistic planner. So here's the big picture of my whole talk. So we're going to model our problem as a stochastic shortest path problem. So we're going to have an initial state and a set of goal states. Then we're going to generate these short-sighted subproblems that basically are going to represent by this cloud. And what we're going to do, we're going to take everything that's outside this cloud in our search space, we're going to throw it away. We're going to focus only what's inside. And throwing away is not a good idea, but we're going to keep some information from what we throw away by adding an heuristic. So we're going to attach to each state on this border of this cloud an heuristic value, and I represent that by the different shades of green here. So the greener, the closer will be to the goal. It depends on the heuristic, of course. Then we're going to solve this short-sighted subproblem, and we're going to get a complete policy for that, so we know we're not going to need to replan there, and we're going to execute this solution. And then once we get to the border of this cloud, we're going to iterate. We're going to do that again and again until we reach the goal of our original problem. And then I'm also going to show what we can say about this single execution case. And also what we can say about if we have a simulator, for instance, we are not executing the real world, and we can simulate this problem from the initial state to the goal state several times. So now I'm going to give a little bit of a background. So this is my definition of stochastic shortest path problems, or SSPs. We have a set of states, initial state, a set of goal states, set of actions, transition probability function, that's the probability of moving from one state to another when you apply an action. And we have this cost function that's going to be the cost of applying action A on state S and reaching the state S prime. This function is always going to be greater than 0, and we require to be defined only if this transition is defined, so if the probability is greater than 0. This example here is going to be my running example. So I'm always going to show the initial state has this gray shade of state, and then the goal state is always going to be green, and I'm going to always attach the probabilities in the arrows. So also, by our optimal policy, it's going to be for us, the policy that minimizes the expected cost to reach a goal state from the initial state S0. And the minimum expected cost to reach a goal state is given by V star, the optimal value function here. That's going to be 0 if you're in the goal state. Otherwise, it's going to be the minimum over the actions of the expected value of applying that action and solve the problem from that state. So here's a little bit a more formal idea of what are short-sighted SSPs. So we are in the business here of managing uncertainty. Our search space is too large. And since we have probabilistic effect of actions, there are some parts of our state space that might be very unlikely to reach. So since it's too large, we cannot look at it all at once. So we're going to consider only the neighborhood of our current state that I'm depicting here by this circle. And we're going to prune everything that's outside and we are going to put every single state in the ring of the circle. We're going to call them artificial goals. So the short-sighted SSPs are going to be SSPs, but they will have these artificial goals. And we're going to attach an heuristic to these artificial goals that's going to tell you more or less what is the expected cost to reach from one of these states, the original goal. And finally, we're going to define the neighborhood of a state using this function delta that basically counts the number of actions to reach one state from another. So delta of S to S prime is just the minimal number of actions to reach S prime from S. Now being completely formal, so if you give me an SSP, you give me one state S, and you give me a value of t greater than 0 in a heuristic function, my short-sighted SSP for these parameters are going to be a new state space, S prime. They are going to define as all the states 0 S prime in the original space, such that I can reach S prime from S, that's one of the parameters, using at most the actions. Then I'm going to change the initial state to the state that you gave me S, and I'm going to change the goal states, the goal set. So now the goal set is going to be all the states S prime that are reached using exactly T actions. So it's going to be all the people in the ring of the circle. Then the structure of the actions are going to be exactly the same. I'm not going to change the actions, I'm not going to change the probability transitions, and I'm going to change the cost. So now the cost of applying action A on state S going to S prime is going to be exactly the same as before, plus the value of S prime in the heuristic if S is an artificial goal. If S is not an artificial goal, is not on that ring of the circle, then we're not going to change anything, right? And here's some examples. So here the running example again, the very same, and here's the delta function from S0 to all the other states. So S0 to S0, you don't need to apply an action. To S1, you can get with one action. To S3, you can get with one action. To SG, you can get with one action. And S2 is the only one that you need two actions to apply. So if we look at the short-sighted SSP, starting from S0 for t equals 1, we're going to get everyone here that has value 1, and we're going to put them as artificial goals. So SG was a goal, we keep it there as a goal, and then we have these two artificial goals, that's why they're dashed. So far nothing really interesting, but if we increase the value of t to 2, then we're going to have this. So now only S2 is an artificial goal. And we keep the original goal because we could reach with 1. And look that now here the back part of that example is represented perfectly. Right? So we have all the action structure here, even though I can reach S3 with more than 2 actions. I could go from S0 to S3 and keep looping here. We still will not count this as an artificial goal because we can reach it with 2 actions. 2 actions, that's the minimum. So you might have a question right now in the back of your mind of, is this look-ahead search, or how does it compare with look-ahead search? So again, the same running example, and here is the look-ahead search from S0 using t equals 2. So what we are doing is, what are the states we can reach using up to the actions? So from S0 we can go to S3 and S3 again, right, on this example, and this is how the look-ahead search works. So now I'm going to replace the original problem here with the short-sighted SSP from S0 and t equals 2. So what happened is, we put this state as an artificial goal. So just staring at the two pictures, you might be able to already say, what is the difference? So the difference here is, look ahead is giving us a 3, while short-sighted SSPs are giving you a graph, or a multi-graph. So, and is this really a big difference? And the answer, yes, it is a big difference. So if you think about the look ahead, once you look at the state S0, it's saying you can go to S3, and then you go to S3 again, but then it doesn't say anything else. On the short-sighted SSPs though, you know that from S0, you can go to S3, and you can keep there on S3 for a really, really long time, especially because the probability there is 0.9. So you know that you can get trapped there. And since the optimal value function is looking at expected cost, so you're in the business of doing these expected values, that once we are talking about loops, they're infinite sums. So what look ahead is giving you is an approximation of this infinite sum by taking the first t parts of this infinite sum, while on short-sighted SSPs, we keep this whole infinite sum. So here, we are simplifying the horizon, and here we are not. We just simplify states, we keep the same horizon, and we keep the structure of actions. So this difference is so important that in the paper we have this proof. I don't know if you guys can see from the back here, but basically what you're saying is, if you compare look ahead from the same state using t, or given value of t, and short-sighted SSP starting from the very same state and the very same value of t, we are going to give you a better bound. We are going to give at least the same value as the look ahead, but if there are loops, we're going to give you a better bound. And since we're talking about cost, a better bound means a larger bound, and both of them are going to be bounded by the optimal value function if you're using a reducible heuristic. So now that I've told you what is a short-sighted SSP, I'm going to present our planner, the short-sighted probabilistic planner, or as we call SSIPP. So SSIPP is a very simple planner. You might even call it a meta planner. So what we are doing here is, you start from your initial state, you're going to generate a short-sighted SSP. You're going to take the short-sighted SSP, compute the optimal policy, and here you can use any optimal solver. You pick your favorite. And you might be thinking, well, you motivated this talk saying that complete policies are hard to get, they do not scale up, but it's okay. The short-sighted SSPs encompass a really small part of your problem, so it's okay to get a complete policy there. And then once we have this complete policy, we are going to execute it until we get to a goal of the SSP. If it's a goal of the original problem, you're done. And if it's not, we're going to iterate that again and again and again. So now I want to show what's a guarantee we can give for this particular strategy of applying SSIPP. That's when you do that only once and you execute this action in the environment. And the guarantee is for at least t actions, you can execute at least t actions before replanning. So basically what you're saying is, since you construct these short-sighted SSPs, looking at all the actions, all the states that you can reach using up to t actions, you know that you're not going to replan if you get a complete policy for them. But that gives you the bound of t. But how we can get the at least t, that comes again by the fact of the loops. So in this example of short-sighted SSP, if our optimal planner gave us this policy on S0 apply A1, on S3 apply A2, we can apply this policy for more than 2 steps. For instance, we can go from S0 to S3 and keep track on S3 for an indefinite amount of time. This again showing that we are not simplifying the horizon of the problem. We can still stay there for an indefinite amount of time. You give me any amount of time, there will be a non-zero probability of getting trapped there. Now, what if we run SSIPP multiple times, right? So there are 2 scenarios. Imagine that I have Robert. The Robert is saying the same problem over and over again. Or the more common scenario is now, instead of executing the environment, we have access to a simulator. And someone gave us a budget on time, saying you have 20 minutes, and you have access to a simulator. You're going to simulate this problem until you reach your budget. Meaning, once you get to the goal of the original problem, you start it again from the initial state. So then we have this theorem saying that SSIPP will be asymptotically optimal. Meaning, if the same problem is solved sufficiently many times, then the optimal policy is always found. And the intuition behind it is, let's suppose that this is the first solution, the first run of the problem. So these are the short-sighted SSPs that we generated. The red line is the execution. We got to the goal. Now when we're going to solve the second time, we're going to get some information about the last execution, and that will help us to change the bias. I'm not so sure if you can see the different shades of green here, but basically the last execution is changing how we are biasing the solutions inside the short-sighted SSP to reach the goal a little bit faster. So if you know real-time dynamic programming, RTDP, basically we are giving the very same guarantees that RTDP gives you. But at the same time, if you know RTDP, you might be asking, well, how does it differ from RTDP? How does SSIPP running on an anytime setting differs from real-time dynamic programming? So both of them are asynchronous value iteration. And the real difference is the scaling of the bound updates or the bound backups. So just to illustrate this difference, let's suppose that every time that I make a backup, I'm going to put a yellow dot here in this search space. So if you look at the RTDP, we're going to basically run one trial of RTDP. We're going to get one path from the initial stage to the goal. And we're going to make backups on this line. And then, if we do another trial, it will be another line. Next try, another line, and you will get the drill. right? After a long time, we're going to cover a huge region, and we're going to extract the optimal policy from this region. So how does SSIPP work then? So we're going to generate a short-sighted SSP, and then we're going to solve it. Let's say we're going to use RTDP to solve it, the very same algorithm that we use in the other side. So we're going to run one trial of RTDP, we're going to do this one short line, because now we're not going to the goal, we're stopping the artificial goal. We're going to do another line, and again, you get the drill. We're going to cover a whole region here. And then we're going to execute or simulate our solution, get a new state, and do that again. We're going to get another block, and do that again until we reach the goal. So the difference is, RTDP, you're going to fulfill this region by doing these very thin lines, while your SSIPP is going to choose a block, solve the block, do a lot of lines in this small block. They move to the next block, do several lines on this small block. And as I'm going to show you in the next slides with the experimental result, this is enough to get improvement in the performance on top of the algorithm that we use as the optimal solver. Meaning, if we use RTDP, we're going to get an improvement on top of RTDP. So, in the experiments, I'm going to compare SSIPP against the winners of the previous probabilistic competition. And the setting I'm going to use it is the setting from the first and the second one, the IPPC 2004-2006. And basically it boils down to the following. For each problem, the planners are requested to solve this problem 50 times in 20 minutes. And learning is allowed between the attempts. So everything that you can infer, or you can learn, or you can keep track of, you can use it again for the next attempt. And the evaluation metric is going to be the number of times the goal is reached over these 50 times that you have to solve it. And here are the planners I'm going to compare with. I'm going to compare SSIPP using LRTDP as optimal solver. I'm going to compare with LRTDP by itself, then FF replan the first place of 2004, FPG first place 2006, or FF first place 2008. And the parameters for SSIPP is I'm going to use T from 1 to 10, and the heuristic is going to be the zero heuristic, FF plus all outcome determinizations, and the mean. For LRTDP, I'm going to give the same set of parameters, except that T I'm going to allow to be from 0 to 10, and for LRTDP, T means the look ahead. So every time that LRTDP has to do a greedy decision, it will use this look ahead. If T is equal to 0, no look ahead, is a vanilla LRTDP. If T is greater than 0, it will use that look ahead search, will find the best lead, and gives a decision on that look ahead tree. So here's the result for the triangle tireworld. So I'm giving you two flavors of SSIPP. The blue flavor here is going to be the same throughout the plots. There will be T equals 3 in the FF plus all outcome heuristic. The green line, the green bars are going to be different for each one of the domains because we are picking the best parameter for that specific domain. For LRTDP, the yellow bar is exactly the same. You're giving the best parameterization for LRTDP in that problem. So what we can see here is SSIPP, the green one, with the LRTDP, the yellow one, both with the best parameterization for that specific domain. SSIPP performs much better. And scale up is much better. You see how we slow down very slowly while LRTDP goes down really, really fast. And the only difference here is how we're scaling our bound backups. And we scale up better than the others. So that was our best case. So here's the other case, Bloxword. Again, we perform better than LRTDP, but what's happening here is the green one changed, as I said, now is 2 in FF heuristic. What is happening is we do quite well until problem number 8. For the larger problems, we just get lost. If you're familiar with Bloxword, there's a ton of non-optimal solutions inside, and we get lost trying to find a solution there. Now, going to the exploding Bloxword, that basically is a Bloxword with dead ends, where blocks can explode. So what happened here, we have an improvement up to problem number 9, coincidentally the same number as the other one. So if you see the problem number 1, we improved upon all the others, a little bit better than LRTDP. In this case, the blue and the green curves is exactly the same parameterization. We improve it, we tie, we never lose up to problem number 10. It's a small tie, maybe not relevant. But from problem 11 and so on, we don't perform well. And what's happening here is the probabilistic interesting part of the problem, once it's done, once the important blocks are detonated, what is remaining there, it's a Bloxword. You have to move the blocks in the way you want, and we know you're not great on Bloxword, unfortunately. And here's the last domain, kind of the borderline of my time. So in zero travel, we improved a little bit upon the other planners. And here's the summary of the experiments. So the blue curve that was SSIPP overall, the SSIPP representation over all the domains, we outperformed all of the other players on 16.6% of the time. We tied with the best on 41%. If we optimize the parameters for each one of the domains, we outperform them on 36% of the time, tied with the best on 53% of the time. There's two interesting remarks here. The first one, SSIPP is never the last place in the planners, meaning you're not going to get the worst performance in any one of the experiments we've run so far. And the very nice one is RTDP never outperform us. So we tie or we do better. So basically what I'm saying here is just changing the scheduling of the data updates about got us improving the performance. So to conclude, I present you a framework that presents this new trade-off between complete and partial policies. And to do that, I introduce short-sighted SSPs and SSIPP, this new planning algorithm that you can use in two flavors. I have two flavors of SSIPP. SSIPP has a replanner where we can give you the guarantee that there is no replanning is needed for at least the actions. And then you can use it as an anytime algorithm that is exactly the very same guarantees that RTDP gives you. And as for future work, we are looking at new definition of short-sighted spacing, that S prime. How can we define that differently? We have already some ongoing work on that. And to improve the scalability on the non-probabilistic interesting problems. For instance, Blocksport, when you have several non-optimal solutions, can we just ignore the probabilistic interesting part of it? There's no dead ends. Can we just get a cheap solution out of that? And basically that is. Thank you.
So in your paper you say that you require the reachability assumption. How is it fair to compare on exploding blocks world then because it has dead ends?
Yeah, so it's the same requirement for LRTDP, right? So in the sense LRTDP we require the very same thing. So with LRTDP we're really fair. And that requirement actually is to find the optimal policy, right? If you don't have that, we are not guaranteed to find the optimal policy. We're not even guaranteed to finish a trial. But in practice, we finish a trial because we have a threshold there in the cost. So if you cannot reach anymore your goal state because the block that you needed, let's say the table exploded, and the table was not supposed to be exploded, you're going to move blocks around. At some point, the cost will be very large, and you're going to say, okay, that's too much, that's a dead end, let's start it again.
Yeah, but if there are dead ends, unavoidable dead ends, your heuristic functions is infinite. So normally, in such a case, the criterion is not well defined. There is no optimal policy. You can choose one.
Yeah. So if there is, that's exactly the case of exploding blocks work. So if you see all this problem here, it's not that we're not getting the optimal policy there. I'm not sure about this first four, but at least the first two, I check it by hand. There is no policy with probability 1 to reach the goal. So what's happening there, since we're not giving infinite cost, we have a threshold. In this case, it's 500. Once you get there, eventually some policies will not diverge to 500, some will, and you don't have time enough for all your policies in your initial state to diverge to 500. So because we have this budget of 20 minutes, we give solutions until you get.
I don't understand something. All policies have the same infinite value. How can you compare policies that are equal to infinite?
Yes, in this case, sorry if I didn't explain well. That's exactly the case of these four problems. All the policies there has infinite cost because there's no probability 1 policy to reach the goal. But the thing is, for these problems, we're not in the business of finding the optimal. We cannot even get close to the optimal. So we don't have time enough to diverge. That's the thing, right? If you give me 3 days, then probably all my policies would diverge. But since we just have 20 minutes, none of them diverged, and we gave as solution whatever we thought was the best for that threshold. But I agree with you, there's no cost to find it. If you see the V start of 0 is infinity in these problems, except let's say the number 5 and the number 7. There are probability 1 policies to reach the goal there.
So do you define a penalty of that essentially? What I recall is the same.
Okay.
Yeah.
Okay. So
Yeah, thanks.
Oh, any questions? Well, hard to go play, actually. Okay, ask while we're switching. You can ask. Ask while we're
When
switching.
you generate your short-sighted SSP, are you computing the heuristic value systematically of the entire fringe of the SSP?
No, yeah. I guess what you mean by systematic is doing it smart. Yeah, we are doing it smart. We are just asking for the basic value where it matters.
Okay.
We are not computing the basic value at all. Then if we think of that after heuristic, it will be really costly. So, we just basically, we define what is the fringe, and every time we touch a fringe one, we query for the heuristic.
Okay, let's let Thomas go. I'm particularly interested to hear about this paper. I've waited 1 year to hear about the winner of the probabilistic. This is here. So I waited 1 year to hear about the winner of the probabilistic planning competition last year, and this is the paper in the plan.
Thank you. Okay, so hello. I'll be talking about the probabilistic planning system first, which was developed by Patrick and myself. And yeah, how did it come to be as it is?